Hi, my name is Shane Sylvester. My final project for this Introduction to Finite Elements course is a finite element analysis of flow over a step. While this will focus primarily on the standard flow over a backward-facing step, I will also include a full step as shown in the image here, which includes a backwards and forward step in the flow path, as if a groove in the wall. This is the most common example of interruptions in the flow field in real life. The flow investigation will focus on flow in Cartesian coordinates. It will also focus on the portion of flow where the boundary layer resides. The flow will be assumed, at least to start, as laminar, fully developed prior to the step, steady state, and two-dimensional. It will also be assumed that the flow is air flow at room temperature conditions to start, with a constant free flow velocity. The model will be conducted with a COMSOL finite element software program, such as the one you see in front. This program will form the bulk of the analysis and the model for consideration on this project. The model will consist of a defined geometry, as seen on the screen, of the flow field, defined properties of the flow, appropriate boundary conditions, and an appropriate finite element mesh. This mesh will be determined over the course of the project's modeling effort to create the strongest possible mesh, with coarseness applied in areas with little flow effects of interest, and high mesh density applied in areas of high interest, particularly around the corners of the flow field. The model will be based on the Navier-Stokes equations, which are the key equations that define flow. These highly complex differential equations are not trivial to solve, and therefore require the use of the assumptions that I previously described and powerful software tools. Due to the complexity of the analytical solution of this problem with the Navier-Stokes equations, the model will have to be validated with a multifaceted approach. This approach will take the use of a more analytical one-dimensional solution for the validation of the free flow field portion of the model. This should show general applicability of the model. The 1D calculation will be found using the Maple program, then compared to the report deliverable. The other part of the validation must rely on empirical data and literature review to confirm the validity of the model. I will work to complete this model, validate it as much as possible, and consolidate my findings into a report deliverable. If there is enough time, I would like to expand this model to include a three-dimensional model with walled boundary conditions on either side of the flow, as it would be seen in a wind tunnel, for example. In addition, I would like to continue this analysis to conduct a heat transfer analysis. This heat transfer analysis may take the form of heat transfer out of the flow field into the surrounding wall, as if it were a hot flow with cold surroundings, or into the flow, causing perturbations of the flow from connected electronics giving off heat. Another potential expansion of this model would be to consider various flow properties, as for a water or helium flow, which would be two other similar test chamber flows. You can see here now an initial model created to show the flow geometry in 2 dimensions. This model shows the basic flow field with the free stream flow at the top and wall geometry at the bottom. As you can see, the flow has plenty of distance to fully develop and reduce any potential head effects. Further development of this model will allow for contour lines of the flow field to depict the vortices that should form adjacent to the steps in the wall. This will all be combined and summarized in the project report deliverable. Thank you for listening to this first project